All right, chapter 3, we're going to be getting into working with exponential and logarithmic functions. And to get our introduction started, we're going to be looking at exponential functions today, both exponential growth and exponential decay. We're also going to take a look at the logistic function, and we're going to take a look at what are some population models that include or work with exponential growth and exponential decay. So starting out with, let's say we have this Lazy Days Island, and Lazy Days Island was established in the year of 2000, and what you go to this island, you don't have to do anything. You do not have to work. You don't have to go to school. You can just do whatever you want. So if you want to lay out in the sun, you can go ahead and do that all day. Well, so what happened in the year 2000, 200 people started this island. Well, since the year of 2000, the population has now increased by 25% every single year. So if we wanted to look at what's happening to this population over time, if we started out at 1 year, so trying to figure out what the population of this island is going to be after 1 year, what most people would do is they would take, okay, we started with 200 people, and then we added on an additional 25% of that 200. So 0.25 times 200, and 25% of 200 is going to give us 50. So I ended up with 250 people on this island after 1 year. Great, so we continue to look at what's the population after 2 years. So now I have to take a look at, well, we have 250 people at the start of the year, and now we're going to gain another 25%, and we're going to gain 25% of that 250, which we end up with 312 and half of a person that it's going to be on this island. Well, this is great, and if I wanted to keep doing this, I could do this step, but what if we wanted to figure out what's going to happen after 20 years? Doing this process here is going to be a little tedious, because when you're sitting here finding the previous answer, multiplying it by 25% and adding it, it just gets to be too much. So we start to look at what's a faster and easier way to do this. Well, this two-step process right here can be summed up in one step. And what we can be doing here is, instead of taking and multiplying and adding, we can do all of this in one step by taking 200 times 1.25. And that will also give us the 250 that we're looking for. So what you're doing here is you're multiplying 200 by 125%. This is including the 200 that we started with and adding the additional 25 people. So then I could take, for the next one here, I could take our 250 and I can multiply that answer times 1.25, and that will give us our 312 and half of a person. So this is great. If we kept doing this, starting out with our 200 and multiplying that by 1.25, we took that answer times 1.25. Now after the third year, I would multiply it by 1.25. After the fourth year, I'd multiply 1.25. I could keep doing this, and if I'm looking for the 20th year, I'm going to multiply by 1.25 20 times. So instead of doing our two-step process here, we can go ahead and say, all right, we started with 200 people, and now I'm going to multiply that answer by 125 20 times. And you're doing repeated multiplication here, so we're working with powers. And now by doing this, this is telling me that I'm going to end up with 17,347 people approximately on this island if it continues to increase by 25% every year. Well, what this is doing here is, this is not a linear growth model, it's an exponential growth model. We're not gaining 50 people every single year, it's increasing by a different amount every year, and that's our exponential growth. So we have two different functions that I'm using for exponential growth here. I have a times b to the power of x, and I have p sub 0 times the quantity of 1 plus r to the power of t. Both of these examples here are identically, really essentially the exact same thing. Because what I'm saying here with my exponential growth is that b, which we call this the growth factor, And that growth factor has to be greater than 1 in order to be exponential growth. Well, how I'm using the function down below here is 1 plus r. What you're doing here is you're taking 1 plus the growth rate. And so if we say a population is growing by 25%, I'm taking 1 plus 0.25 to get my growth factor that I'm looking for. And then you have these values that are outreach in front here, the a and the p sub 0. These are our initial values. It is what are we starting with? So maybe we are starting with a population of 200 people. Maybe we're starting with a bank account that has $500 in it. That's going to be our initial amount. And when we think about the graph of an exponential function, our initial value is always going to be our y-intercept. It's what's happening when x is equal to 0. So here's our exponential growth, just to kind of get an idea about the initial value in the growth factor and seeing a couple examples of this. I have 2 examples of some exponential growth functions. And so by looking at both of these, I know that they are exponential growth because the growth factor is greater than 1. Now from this, I can tell a couple of pieces of information. And first of all is looking at that value of a. And what that's doing here is it's telling me what the initial amount is, what the initial population is, what the initial dollar amount is going to be in a bank account, what the initial amount maybe is for a credit card payment of something that's going to be due later on. So here when we're talking about the initial amount, I'm looking at my initial amount being 6 for the first function here. And then for the second one, we would say that that's going to be 7. Now to figure out what our growth rate is going to be. Now there's a difference between the growth rate and the growth factor. Our growth factor is 1.243. Now our growth rate is going to be looking at what are we adding on to 1, because 1 plus r is what is giving us in our growth factor. So if I think of here as 1 plus r is equal to 1.243, I know that if I subtract 1 from both sides, I get 2.243. This is telling us that our growth rate is 24.3%. In the next problem here, if I did the same thing, taking 1 plus r is equal to 1.021, subtracting 1 from both sides, this is telling me that my growth rate is going to be 0.021, which as a percentage, that's giving me 2.1%. So there's a difference between our growth factor and then our growth rate of what it's actually increasing by. So there's our exponential growth. Now we're going to take a look at an example of exponential decay where we have work all day island. So completely the opposite of lazy day island where you work 24/7. You are constantly doing something. This was established in 1995. People thought it was a good place to go because it was on the beach. And then all of a sudden they realized that it's not all that fun and dandy. So they started leaving that once they discovered Lazy Day Island. So in 1995, there were 10 million people that were on this island, and it has been decreasing by 40% every year since then. So if I wanted to look at what the population is going to be after 1 year, I'm taking this 10 million people, and I'm going to this time be subtracting the 40% of that 10 million people that are there. And when I do this, I end up with 6. Not 6 people, but I have 6 million people that are left on this island. After 2 years at this rate, we're going to take that 6 million people that are there, and then we're going to be subtracting 40%, subtract 40% of that 6 million people, and then we would end up with 3.6 million people. So 3.6 million would be 3,600,000 people that would still be on this island. Well, just like when we were looking at the Lazy Day Island, is what happens if we want to figure out how many people are going to be on this island after 20 years, because maybe it'll be extinct by then. So as we look at this, I could keep doing this two-step process, but that gets to be a little tedious. So we look to see how can we take these two steps and lead it into one. Well, here's where we can be taking it, well, what's left over? If we're subtracting, we're taking away people, what are the people that are still left on the island? So if 40% of the people are leaving, that's leaving 60% of the people still on the island. So by taking 10 times 0.6, this is telling me here that I'm going to have 6 million people on the island. Of that 6 million people the second year, if I look at 60% of that population, now I have 3.6 million people. So we started out with our 10 million people, and then I multiply it here by 60%, and that's going to tell me how many people are on this island year after year after year. So by continuing with this for 20 years, ultimately here I'm multiplying by 0.6 or 60% 20 times. And once I finally do this and calculate it out, I get 0.000219 million people. Now you might say, oh, that's no one's left on this island. Well, because this is in the millions, this is leaving us with 219 people that are still on the island. So this is giving us our example of exponential decay. Like exponential growth, it looks very similar as far as the functions go. Here, a times b to the power of x, but we're going to be careful because our value of b is going to be between 0 and 1. Okay, it's got to be less than 1, greater than 0. We will not be working with negative growth factors at all. We want just positive growth factors here. And or you can talk about the growth, the decay rate, I should say, and the decay rate by taking 1 and subtracting that value. Like exponential growth, our initial value is always going to be that value of a, or the initial p sub 0 value. So that's going to be where our population or where our bank accounts are going to begin. When I look at an example of two exponential functions here, when I look at the initial value, that's going to be what we're starting with. I'm just going to abbreviate that here. We end up with 3 and 5. Then when we take a look at the decay rate, so again, I'm looking at the decay rate, not the growth factor. So now if I look at this, I'm looking at 1 minus r is giving me 0.42. So if I subtract 1 from both sides, that gives me negative r is equal to negative 0.58. Divide by negative 1, and we get r is equal to 0.58. So we're talking about here having a decay rate of 58%. That's what it's decreasing by. If I want to find the decay rate of the growth, I could say the decay factor of 0.03, 1 minus r is equal to 0.03. Subtract 1 from both sides, negative r is equal to negative 0.97. Divide by negative 1, r equals 0.97. And I know some of this is math that you can probably do in your head, but I just want to show you where these values are coming from. And we get a 97% decay rate for our exponential decay. So exponential growth, exponential decay, we can use it all based off of this same function here of a times b to the power of x. Both of those functions have an initial value of a, and then exponential growth for when your growth factor is greater than 1, exponential decay when your growth factor is between 0 and 1. So there's our exponential growth and exponential decay, and hopefully I can keep this under 20 minutes. I know I'm hitting that 15-minute mark, but I do want to finish up talking about a couple other exponential functions that we're going to be looking at. And the first one is talking about continuous growth. This one's going to come in once we start looking at using some banking examples and some financial examples of when we have continuous growth. What I mean by continuous growth is that we are applying this growth rate all the time. So rather than saying that the population is decreasing by 20% every single year, we're going to be saying, okay, it's decreasing by 25% continuously. So we are constantly, people are leaving. So it's not like it's just one lump sum. It's it's constantly happening over a period of time. So by doing that, we start to look at this whole idea of, in this example here, I'm talking about growth, 1 plus 1 over x, because this x here is going to be your rate at what's happening. And as that rate increases, so as or the number of times, I should say, as the number of times that we are applying this growth rate increases, what ends up happening is our function here is going to go to this value of 2.71828. And the limit as x gets really big. And what that value is that is the number e. And so here, when you're working with continuous growth or even continuous decay, we will be looking at a times e to the power of kx. And what's happening here is now k is our growth factor, or growth rate, I should say, or decay rate. And if that value of k is greater than 0, so it's a positive number, we'll be working with exponential growth. If that value of k is less than 0, we'll be working with exponential decay. And so this is going to be an example that we'll kind of be looking at, and this is talking again if there was continuous growth or if there was continuous decay. And we'll be talking more about this limit later on once we start using it in the financial part of exponential growth and decay. And then the other function, which this is the first time you've probably seen this one, but we introduced it when we talked about our 11 basic functions, and that is the logistic function. Now, some of you might look at this function and say, well, that's not exponential growth. Well, it actually is because it's constantly growing, but what's happening is a lot of times as time goes on, things plateau. Okay, a population of an island, well, we can't keep growing. Eventually, it's going to have to hit a maximum amount as far as how much room is on this island. And so that's what the logistic function is allowing us to do. It puts a cap on it. So we have a couple different functions that are going to be used. And if you're working for a growth model for a logistic function, I have this value of c over the quantity of 1 plus a times b to the power of x. Now, with this function here, when it's going to be growth is when b is between 0 and 1. So that might seem a little opposite, but here we're talking about growth, a logistic growth. Or if we're using a continuous rate here, if we have e to the power of negative kt. So here, when you have a growth rate that's going to be between 0 and 1, we're actually going to have growth for a logistic function. And when you look at this function here, what ends up happening is as x goes towards negative infinity, our limit is going to go to 0. We have a horizontal asymptote along the x-axis. And as your limit goes to positive infinity, what we will have here is another horizontal asymptote, and that's going to be at the value of c. So whatever value we have in our numerator, that's going to be the maximum that we can possibly reach. For looking at decay, so logistic decay here, here's our two functions that we're going to be looking at. And you can see that this is a reflection over the y-axis. We are going to have a maximum value of being at c. So here, this time, everything's being switched. So as the limit of x approaches negative infinity, we're going to be going towards c. And as x approaches infinity, we're going to be going to 0. So these are two functions that I definitely suggest that you write down. I'm not going to make you memorize these. I'll have them written on a test just because they're not used as much as like the exponential itself. But we should be able to recognize of when it's going to be growth and when it's going to be decay. So if you have any questions on anything, make sure that you are writing them down so you can bring them up in class. But otherwise, we should have a good idea of what exponential growth and decay are, and then also looking at those population models that we did. That's it.